Okay, cool. So I hope I didn't overpromise too much in the message. Um, I I did make a long list, handwritten with all the requirements, and then wrote solutions for all of them down and could check all of them off in my head. But then I made those slides yesterday and today, and I did notice a couple of holes in it. So there are still, it's not a solution to everything. There are still a couple of open questions with what I'm proposing, and also not everything I'm presenting here is stuff that we already agreed on. So I'm going to start with the stuff that we already agreed on for the most part, and then clearly separate where I'm kind of starting to put together ideas we discussed but haven't really settled on yet. But I think if we pull in those ideas we previously discussed, they could solve almost all of the issues we have, or all of the problems we are trying to solve. And the main open questions are around where this would exactly be happening in neuroanatomy, and like some more mechanistic questions around matrix cells and other aspects of it. So
That sounds promising. Because yeah, I guess that's the, in some sense, less important issue.
yeah, yeah. So
Uh,
really, it would kind of address like on a conceptual level most of the or pretty much all the problems we discussed. Um, so it is a bit of a dense presentation. I really spent a lot of time trying to make it digestible, um, and yeah, kind of putting everything in reference frames and making it visually useful for people to understand where I'm trying to get at, but still it's partially some kind of complex ideas. So just, yeah, feel free to interrupt and ask questions whenever. And yeah, we can discuss everything. So yeah, chapter one. I'll start off
Chapters,
with
whoa.
just, yeah, there are 4 chapters and an epilogue. So chapter one is the problem and constraints. So just kind of going through, yeah, the problem space, which isn't a trivial thing. It's like, I feel like half of the time we spend talking about just the problems we're trying to solve and all the different aspects of the problem. So I just try to put together a complete list so then we can check those off in the next chapter with the solutions to make sure we're actually solving everything.
You may not remember, but in my book, I said that the way to solve problems, defining the problem. If you define the problem sufficiently, the answer presents itself. So I'm agreeing with you. It's like if you really got the problem down, then the answer's obvious.
Yeah.
You spend all
Yeah, I
this
was
time
just
trying to understand.
talking to Will yesterday about how, like, in the beginning when I started at Numenta, it would be like kind of frustrating. You would think, oh, this would work, and then you would come in and be like, no, brains can't do this. This couldn't, like, maybe you can do it in a computer, but then, and it in the beginning be frustrating, but now it's like, oh, that's great. We have one more constraint to find the optimal
Right.
solution. Like each of those
Exactly.
constraints actually helps us narrow down
Right. Yeah.
the solution. So hopefully, yeah, this is helpful. Um, okay, so number one, we want to learn a model of object behavior. That's kind of the task we set out to do. So there are tons of objects that move, and we want to be able to learn those behaviors. And with that, we want to include any arbitrary change in features and morphology over time. So it could be something moving, it could be something changing features, color or brightness, could be something moving in like multiple directions, multiple degrees of freedom. There could be multiple objects moving dependent on each other. It could be like a compositional object moving its parts in a coordinated way. So there are lots of different versions of behaviors, and we want to be able to model all of them with one mechanism. And also, we somehow need to be able to observe all the changes such that the model can be learned in a column. So either like following the movement or saccading around or having like many sensor patches covering the object. And we talked about all of those before as well. And I'm not going to go into too much depth on this one because it might be like a combined solution. of intelligent policies and voting. And then second, after we learned a model of a behavior, we want to be able to use that model to recognize object behaviors. First, we want to be able to recognize the behavior on an object, on the same object that we learned it on. So we learned the stapler moving up and down, and we want to recognize it again when we see it. But also we want to be able to recognize the same object behavior on a different object. Like we learned the stapler, and now we can also recognize that behavior on the hole puncher. And like the extreme example we talked about before is like the walking or dancing banana. It's certainly something you've never seen before, but still you can recognize that the banana is running, and you can imagine a dancing banana without even ever having seen one. So brains can clearly mix and match these object and behavior models. We also want to be able to apply a behavior to an object at an arbitrary location, orientation, and scale. So we might have learned a hinge behavior, and then we can apply that to a door or a laptop or any kind of object that has a hinge on it and opens and closes, or a book. We also want to be able to recognize where in the behavioral sequence we are. So if we see a closed stapler or an open stapler or a wide open stapler, we want to know where in that kind of sequence we are. And we want to be able to recognize the behavior at different speeds. So we might have learned this kind of speed of stapler, but then we can also recognize it faster or slower. And we want to be able to do this with single or multiple columns. I put a question mark there because it's maybe a bit questionable how well we can do this with a single column. At least for more complex behaviors, like very simple behaviors, like just pushing down a button and recognizing that with touch should be possible with one column, but anything more complex and fast moving might require multiple columns. Next big topic. So those are kind of the first ones that we talked about a lot and that we kind of have a solution for. Now I'm going a bit more into additional things that came up lately. So
can I just comment on the multiple column idea?
Yeah.
In my mind, a single column should, in theory, be able to do everything, but practically it may not be able to do everything. I don't think we should be thinking like multiple columns are necessary for distributing the knowledge of the movement or distributing the knowledge of the object.
Yeah, right. Yeah, no, that's why I'm saying like a simple behavior like pushing a button and recognizing that from just touch needs to be able to be learned in one column because we are only getting touch input to one column as well.
Yeah.
But if there's
I don't want anyone to feel like, you know, this doesn't violate the columns hypothesis that columns all do the same thing. It's just that practically you might need many columns to do this.
Yeah, like
I'm done.
Yeah, like we could almost phrase it as kind of a magnitude thing that like in terms of the efficiency of learning, there comes a
Right.
point where a behavior will be so complex that in theory a single learning module can still learn it, but it would take so long to
Right.
revisit all the parts and stuff that it would just practically be kind of pointless.
Right.
But it's the exact same mechanism. It just is faster.
Yeah. Yeah, and here I'm even just talking about inference, so recognizing it again, where it's probably hard if you have like more global movement, like a person walking. If you just have one column and the movement is rather fast, it's hard to see enough changes relative to each other to recognize.
Well, again, if it's moving fast, right?
Yeah.
That's the point. Right.
That's maybe something to try at the next retreat is straw vision and those like random dot movement things. Just given enough time, do we recognize it?
I don't know.
Yeah.
Anyway.
Okay, so next bigger topic, so learning associations between objects and behaviors. So one, if I'm seeing a static object, like I see the stapler and I've learned the behavior of a stapler before, I know that I can push that stapler down. I have an association between like this object can move in that way. I learned that, and like how is that represented? And then second, also seeing the behavior can bias what object we infer. That's kind of the example we talked about before, where we don't have any features of the object itself. We just see movement. In fact, if you show a frozen frame, you don't know what it is at all. But if you see it moving, you can infer that this is probably a person. And then also one object can have multiple behaviors. The stapler, you can like reload the staples, so you can change the deflection plates, all this stuff. Apparently there are these really funky staplers where you can rotate the top part so you can staple it at an angle. So yeah, lots of objects have many behaviors. And then also a behavior can be in an arbitrary location, orientation, and scale on an object. So we already had the kind of opening and closing behavior that can be at different location, rotation and scale on a book or on a door. Here's a mailbox that can also open and close, but also this kind of lever can go up and down at a different location on that object. And we want to be able to assign behaviors at any location, orientation, and scale on an object. And then another larger topic is making predictions about an object at an arbitrary point in the behavior sequence. So basically, we have a model of the object, we have a model of the behavior, and then using those two models to predict if I move my sensor from here to here, what am I going to sense here? So that's kind of using the behavior model to make predictions about the morphology at any point in the sequence. And we want to be able to do that for an object and behavior combination we know, and then also for a behavior applied to a known object. So a new combination. So we learned the stapler and its behavior, and now we want to apply that behavior to a book, for which we've also learned a morphology model, but we've never seen a book open and closed. So there, again, we want to predict if I have my patch here and then move up here, what am I going to sense? And yeah, I just added this note here that when either one of those two models is not learned yet, no predictions should be possible. So if I have never seen the hinge behavior, I shouldn't be able to predict anything on the book opening. If I've never seen a book before, I will first need to learn a model of the book before I can make predictions about how it will look when it opens and closes. And then another constraint we added is that we don't want to be learning keyframes or like snapshots of the object's morphology, where we have to store how the object looks like at different points in time, because we already know the object. It's not like once the stapler opens a little bit more, I have to explore the whole stapler again and learn a morphology object again. And then once it opens a bit more, I have to explore it again and learn a morphology object again. It's like, I know how the top of the stapler looks like. I don't need to relearn it in every orientation. And then also, if part of the behavioral sequence is occluded, we're still able to make predictions about what we're going to see once it comes out of that occlusion. And then finally, this one we haven't really talked about yet, but I just thought of it when I put this together, and I think it's relevant, and what I'm proposing also solves it, is that we want to be able to use the behavior model to compensate for object movement when we're trying to recognize morphology. So if we're having a moving car, it's moving, but we can still recognize the car. So we can compensate for the movement of the object when recognizing the object, and the same with like subcomponents. As the stapler is opening and closing, we can still recognize the top of the stapler and use the kind of behavior model of how the stapler top is moving to compensate.
I don't understand. I don't understand this point. Can you just try again one more time?
Yeah, basically being able to deal with moving objects when we're trying
So the whole object is moving.
Yeah, or components of the object.
Oh, or components of the object.
How does it differ from for behavior applied to a known object?
So this is for inference of the object. Now this is like the morphology of the object. Like we're trying to recognize the car, or we're trying to recognize the stapler. but the object itself is moving because it has some kind of behavior.
Okay, so to me, the car driving, I guess, I mean, that's a funny behavior because the morphology of the car is not changing necessarily at all, right? It's just changing its location in the world.
Yeah, so this is more like the car is moving in the scene of the world, and here the stapler top is moving relative to the stapler
But isn't
bottom.
the stapler example already been taken care of earlier? Or didn't you already talk about the needs of that, which is the need to get rid of
Yeah, I guess it kind of feels like if we can predict what we will see at a location, given the behavior, then that kind of directly enables us to infer the morphology, if that's not already known
Yeah, so the
when it's
solution
moving.
kind of straightforwardly comes out of this part. So it's not like it's a huge additional problem. It's just
yeah,
something that
I don't see it as something different, I guess. That's my question. So but maybe it is. I just don't understand it.
yeah, I
we haven't.
guess I thought of it as different because like when we talk about our larger next capabilities of Monty, we talk about like modeling object behaviors and dealing with the dynamic world. So dealing with a dynamic world where objects might be moving doesn't necessarily require modeling object behaviors. So you just need to compensate for the object movement.
Oh,
And
it's interesting. I mean, it's a couple of things. Imagine take a car, like, or just take something on my desk right here. I can move my coffee cup in different positions. I don't consider that any kind of behavior. However, a car going through an intersection that's a model of an intersection of which there are things called components called cars, and they follow certain paths and certain behaviors. I don't expect a car to jump over the median or so in that case, I can say, oh, it's a behavior of the intersection. Cars are a component of the intersection and they have exhibit certain behaviors. But just physically moving something in different positions doesn't seem to be a behavior of anything. Does that make any sense? I guess.
yeah, no, I agree with that. I think it's maybe just a linguistic.
Yeah, maybe one way, if I'm understanding kind of what you're saying, is like it's kind of a special case of behavior where you can imagine we can have an object in a behavioral state. So let's say someone says the stapler is open, and we can predict like what we will see as a function of the behavioral state. But then while the object is in the process of moving, there's an additional compensation that's necessary. Is that kind of what you're saying?
Yeah,
Like
maybe
it's not just that there's a behavior, it's the fact that there's actually movement going on that presents an additional challenge.
yeah, maybe the slight difference is that in this scenario I'm thinking of here, we haven't actually recognized the object yet. We just recognized the behavior. So we're just
Yeah, okay.
recognizing
So
there's
it's more
something
about the
like,
initial inference. Okay.
yeah, it's like we're still trying to recognize
Oh,
the stapler.
But
while
then it feels like it's kind of the same mechanism, but then just over the hypothesis base.
but isn't that just like the motion capture dots? Isn't that the same idea? You capturing parts of the behavior and that tells you what the object is?
I guess in the motion capture dots, it's not possible to really recognize the morphology because there are no clues about morphology.
Well, you certainly infer the morphology and then you can look for it. I mean, it's like you know, like oh, there should be a human there, right? Or a person. I guess everything up to now completely made sense to me. This last point is a little confusing to me. So the question is, is it worth spending more time on, or should we just
Yeah,
say,
maybe
hey,
it'll be clear later when you
Yeah,
talk
I
about
think
it.
to
it's not that big of a deal. It'll be like a
Okay.
short last comment in the end,
Okay.
and it
All
will
right.
just be
Let's leave it
explanatory.
at that then.
Yeah,
If it's not critical to the argument, let's keep going.
yeah. And so then lastly, just to note that in this presentation, I'm not going to talk about how actions relate to behavior models. So how we use this behavior model to interact with objects or to know how we can interact with objects.
Oh,
So that's
damn!
not something
I hope you're going to solve everything.
Yeah, well, I'm hoping to solve all of these here, but actions, I
Okay.
guess, will be the
I'm
next.
joking.
These slides are awesome, by the way. I love all
Yeah.
the visualizations.
Thank you.
This is like a great presentation for some conference.
Um,
Okay.
That's just chapter 1.
Yeah.
Yeah, does that all make sense? Did I forget about any problem or constraint?
Gosh, I don't know, but it seems pretty good.
Okay, we can bring them up
Just
later.
there's certainly enough in there to hang your hat on, so.
So yeah, if someone's watching this video on YouTube later and you haven't seen the solution yet, you can pause the video here and try and solve the puzzle yourself.
Good luck with that.
All right, so chapter 2, solutions we have so far. So my plan is to go through each of these points and then kind of check them off. But as a prerequisite, I just wanted to revisit our current theory, or pretty quite confident, stable theory about modeling and recognizing objects, like the morphology model, just as like a baseline, because a lot of the ideas for object behaviors are then based on that and are just slight twists on that. So I think it's good to recap briefly. I'm also trying a new visualization look. I spent like all day yesterday trying to get all the information in some way that doesn't look super confusing. All right, so we have the input from the sensor that goes into first order nuclei of the thalamus, and there that consists of some movement information, which goes into like the border between layer 5 and 6. And informs updates the location in the object's reference frame. And then we have feature inputs where we have like feature orientations, like oriented bars, for example, in V1, and also like non-orientation dependent features like color or temperature or something like that, which go into layer 4. And then we learn associative connections between these features at locations in the object's reference frame. And that's really where the model of the object is stored in these connections. And the model of the object is then basically features at locations relative to each other. And over a series of movements, sensing and moving, sensing and moving, we can then narrow down what we're sensing and pool this into a representation of an object ID, which can then be communicated laterally to Voton to kind of narrow down which object we're sensing faster. And also the object ID can be sent forward through the classical feed-forward pathway from layer 3 to layer 4 of the next higher cortical region. And just another point to highlight again is that this location here is unique to the object. So any location SDR that you have here only exists on this specific object. It's not like an XYZ coordinate frame that we use for all of that's used for all of the objects. It's unique to the object. So looking at this location already could tell you which object you're sensing. But the movement input and how you move through that object's reference frame is universal. So movement to any object's reference frame updates it in the same structured way. Does that all make sense? Is that clear for everyone? I mean, probably, but if there are questions, that would be quite important to resolve. No, okay.
I feel like you've just taken 10 years of my life and made it seem like you can do it in 1 minute.
Yeah. It's definitely something that needs to sink in, and it's not easy to arrive at, but now it looks really elegant and simple, so that's nice. I hope that like the future slides will look as elegant and simple in the future as well.
Well, that's our goal, right? You know, goal is always in hindsight, the theory should be sort of should be obvious. Like, oh yeah,
Yeah.
how could it not be that way? But I
Right,
figure it
yeah.
out, the hard part.
Okay. Oh, lastly, we're also inferring the orientation of the object, which is represented in layer 6b. And this orientation can then use modulatory backward projection to the thalamus to basically transform the movement and the feature orientations that go as input into the column, so that we're basically transforming movement and sensed features from the sensor's reference frame into the object's reference frame. And that way we can recognize any object at an arbitrary location and orientation in the world. Right, that should be all.
I'll just point out there's an existing question about the nature of the reference frames into 2D, 3D, ND, which not being addressed here, but we just put aside because it doesn't seem to be essential at this moment in time.
Right, yeah.
We may have not discussed this before, but is the scale also, do we agree that the scale might also be represented in the column and then sent back to the thalamus to scale the movements and the features?
Yeah, so that's the idea. Scale is something that we haven't really decided on where exactly it happens, but the general mechanism should be similar to, like, the conceptual mechanism should be like for orientation, that we can scale the incoming movement vector by whatever scale we're detecting the object at, and thereby recognize it at varying scales.
Yeah, and we have a working hypothesis about the mechanism for that, right? Which is this changing frequency of the background frequency. So we don't need to go into it here, but it's not like we have no idea. And that would occur in the thalamus. It believes that the theta cycle, whatever it is coming from the thalamus.
Yeah, and then I guess just for context, there would be additional scale invariance from columns across the hierarchy, where columns at higher levels tend to have larger receptive fields and tend to be biased towards recognizing larger objects.
Right.
But so that's less flexible. So within a column,
right,
it can kind of, given sufficient time, a bit like rotation, sort of arbitrarily scale the inputs to kind of recognize it.
Right. There's an assumption that different columns, of course, get different inputs and different motor inputs, but within, like, in vision or touch or something, they have inherently different scales of movement and feature sizes, and that's inherent, right? It's not really, it's adjustable within a range, but built in.
Right.
For a complicated sensor like vision, is the information that's flowing the location and the features, that would be like a cluster of features and a cluster of locations?
Well, I don't know what you mean by that, Michael.
I just, like, if you're looking at it with your eye, you're going to see multiple edges, multiple regions of color.
Right. Well, this is a single column.
Okay.
And so this is one column sees just one small patch of the retina, and it's just modeling what it can from the input from that small patch as that small patch moves.
Gotcha.
Obviously, many columns would be observing different parts of the object at the same time, and they would all be doing the same thing, but with a different location, different features. In the retina, the movements tend to be coordinated because the retina moves as a whole. But if a touch, for example, your fingers and the different skin parts can move independently. So that's the more generic solution, is that each column is just sort of oblivious to what the other columns are doing. Each column says, I just see some little patch and I'm moving around, and that's all I know about. And I'll build models, and maybe my neighboring columns are doing the same thing, but I don't really know that. All I know is we can vote on what we think we're agreeing to. So a single column is a single feature, a single movement vector.
Yeah,
I hope that helps.
that's a good thing to point out again, that this input here is just a small patch. It's not like a full image like you think of when you think of computer vision. And all of this happens through a loop of sensing and moving and sensing and moving. Okay, I'll move on to actually object behaviors now. For this brief recap. So now this part about learning to model a behavior and then recognizing the behavior again. That's kind of what we, the idea we had during last retreat. So you should all be familiar with that as well, but just to show it in this new reference frame. Basically, we get again input from the sensor. First we have the movement of the sensor, which is basically the same movement that goes into a parallel modeling part of the column. So I'm showing now kind of shaded. Light blue is the modeling stream for object morphology, and light purple is object behaviors. And you'll see a lot of parallels between these two. So like the object morphology model, here we get a movement vector input of how the sensor moves, which updates the location in the behavior's reference frame. Same mechanism, but separate reference frame from the object's reference frame. And then we also get feature input. But in this case, so in the previous, in the object model, we get static features as input. Now here we only get input when feature change is detected. So when the sensor patch detects some movement or some feature changing or rotating or anything that's actually changing, not something that's static, then the input goes in here into this behavior model. And just like with the object model, we learn associations between locations in the reference frame and changes. And then another thing that's, this thing now that's different is that we also have a temporal component to object behaviors. So here the working hypothesis is that matrix cells in the thalamus could broadcast a global timing signal to this column, which can be picked up by these apical dendrites of pyramidal cells in layer 3. And then the model of the behavior is basically changes at locations over time. So at each time point in the sequence, we're storing changes in that behavior reference frame. So in this case of the stapler opening or like the hinge behavior, it would be the change that's detected as movement of an edge and like rotation of that over a temporal sequence. And then that same as here, this can be pooled into a behavior ID representation.
And maybe just to clarify, I think we sort of touched on this, but just with a stapler, in general, any given location is associated with one change, but you could have behaviors where a particular location would be associated with different changes at different points in time. And that would, at least in theory, be covered here by the apical input to the L3 cell being different.
Yeah.
And so you would
like
predict
the
a
stapler
different
could go back down
change.
to-
Yeah, the stapler could be closing and it would be the same location.
Yeah, or that, right.
Right,
Yeah.
right. So
But so yeah, so I don't know if we've kind of gone through and just checked that like the kind of numbers make sense, but at least in theory that seems like it would work. Like just in terms of how many potential predictions you need to, yeah, I don't know. I'm sure it's fine.
I think it will. I'm pretty confident the numbers will work out, but it's a good idea to think about it.
So quick question here. So this pooling that we have for behavior ID, this would be over space and time, right? This would be pooling because we have these movements at little patches in space, and then we're also pooling over time.
Yeah.
Right. But even the morphology model pools over time, right? It's a temporal pooler. That's what it is. So it's like you can only sense one piece at a time, therefore you're pooling multiple sensations. Here you're pooling multiple changes over time. So in that sense, they're both temporal pooled IDs.
Right. Yeah.
Yeah, it's
Although
like I guess it's
time-
temporal from the point of view of the neurons, kind of.
Right. In the case of the behavioral model, the time is actually a part of the model. It only flows one direction, and the changes have to occur in that direction. Whereas with the morphology model, you could touch the object at different order. So there's an order doesn't matter. It's independent of the order.
Yeah,
Okay.
and then one other thing to highlight here, which is kind of the key idea that solves all of these problems of mixing and matching objects and behaviors, is that one, these are two separate reference frames, and those are completely separate models. So this behavior model knows nothing about staplers, even though it has been learned by observing the stapler opening. And this stapler model knows nothing about this hinge behavior. So this one just models movement over time, changes over time, whereas this one models static features at locations. So like what's the color of the stapler there? What's the sense point normal at that location? What's the curvature sense at that location? So those are really two independent models. And we can now apply or recognize the same kind of movement sequence of changes on any other object that moves in that regular path. So if you open a book now or something else like that, you would still recognize this behavior, even though you've never seen it on that particular object. Does that make sense?
Would it be reasonable to say that the behavior, it doesn't know about the stapler, but it knows about an edge moving, because these movements are arranged in a specific way that mimics an edge?
I think it doesn't know. There's no representation of edge. It's a set of points that you and I could say, oh, that's an edge. But just like the morphology model, Rami, in the morphology model, there's a set of point normals and features. There's no actual separate representation for edge. It's just a set of features that you and I would look at and say, oh, there's an edge. And I think that's the same with the morphology, with the behavior model. It's just these independent points and how they're moving. And on the stapler, it looks like an edge, but other object, it could be a changing circle or a weirdness, and so there is no independent representation of edge. I think that's the key point.
Yeah, like maybe if that was to emerge, it would just be through hierarchy and compositionality, where like if the input was represented as like, yeah, exactly. So it's that's what I mean. So it's like a separate object, and that therefore it can be represented kind of as an entity.
If the world had edges as independent objects, so then it would be an object. But there's nothing edge. It's just an object we've labeled that these set of features we're going to call an edge. But you can have another set of features that's a slight arc or a search that's a curlicue. It doesn't, all equivalent.
So in that case, it seems like given that the features on an object for any given object are restricted to a certain subset of possible features, could help narrow down. It might help with the quicker association with the behavior itself, because if the behavior itself was also dependent upon the input features that generated the behavior, then that gives us some way to build the associative mapping. Would that be accurate?
Yeah, maybe I'll show kind of the proposal for that associative mapping, and you can see if that makes sense, because it doesn't require any like dependency of these two. I mean, it's like said before. I mean, to recognize this behavior, you need to be observing an object that has these possible changes, like that is able to move like that. But it's not like this is storing anything about this object itself or about the features on this object.
You've now
go ahead, Michael.
You've now moved to a set of features, I think, from a single feature.
No.
So this is the behavior of a single feature.
It's like the morphology model. There's lots of locations in the model that would have changing features associated with them.
Yeah,
theory,
so this would
no one
say
can observe all those at once.
Yeah, so this would be like at this location, we observe a movement, and at this location we observe a movement, and at this location we observe a movement. So these are in a reference frame. These are relative changes to each other. So this is like, that's what I try to visualize with these arrows.
Yeah, I'm just getting
and-
at, but so does the single sensor observe those multiple changes at multiple locations at the same time?
No,
So this is
only one
this
at
is
a
one of the
time.
well, this is one of the problems we had, Michael. In the morphology model, you can take your time to move over the object all the time in the world to discover what the features are, and you do one at a time. In the behavior model, the thing is changing, and if you could, in theory, a single column could sample all the points really quickly and say, okay, at this point it's moving this way, this point is moving this way. Now let's go to the next step in time. And this point is moving.
Yeah.
And so the model itself contains all that information, but only a point in time can be sensed by a column at once.
So,
And that
so
was
you
one of the-
risk like shutter lag where
right.
if
In
you
fact,
take an image of a
I don't know if Viviane's going to solve this problem, but one of the real problem is pointing out that you can't really learn it like this. I mean, in theory, the column could, theoretically, but not practically. So that's an issue.
And yeah, like I guess related to that at the retreat, two of the things we talked about was like, yeah, I guess voting can help maybe to some degree, because then you can kind of get a quicker sense of what is the state of the object as a whole. But then also just this observation that like children, when they're learning behaviors, they just do things like over and over again, like whether it's
Right,
just
but
like pressing a
they
button
do,
or like
but I still
oh
argue
yeah,
that,
opening the stapler, or yeah.
but there has to be, I've argued, and maybe Viviane's going to come this direction or not, I don't know, but that there needs to be some sort of shared learning. That is, if every column has a model like this, they all can't learn it independently. So somehow they have to share their knowledge, that I learned this part, you learned that part, let's combine them. I don't know. I mean, that's a hypothesis. I don't know if that's true, but
Or-
it suggests.
or I would go like retained state within the column, but I don't know how that fits in the overall
Anyway,
picture.
maybe Viviane's going to solve this problem, so I don't want to talk.
Yeah,
too much
I think
about
what
it.
you're saying, Michael, that's more kind of like voting, if I'm saying what whereas
Okay.
what I think Jeff's talking about is like almost like weight sharing in CNNs, where it's like
Yeah.
a column would somehow actually transfer knowledge to another one.
So that collectively you could sample multiple points.
Right. You
Yeah,
can't
I
expect every
mean,
column to observe every feature on every location at every point in time. It's hard to do. But
yeah, I'm not gonna get into that too deep in this presentation. I have it in the kind of open questions and potential solutions section, but I kind of assume that for learning the behavior, we can't really use voting, because voting just tells us about the behavior ID. So that just helps for a quick inference when we see an object behavior. But then for learning, I mean, honestly, I think like, I mean, I'm seeing Link all the time repeating a behavior for like an hour today. He spent just opening the teapot and closing it and taking the strainer out and putting it back in, really an hour, just doing it over and over again and figuring out every part of the behavior of the teapot. So I feel like that might just be how it has to be done. And then there are not that many behaviors we learn later on in life. But
all right, we'll see.
yeah.
Okay.
I'm
Yeah, it'd
doing
be
my
interesting if
normal
there's
fidgeting, repeating a behavior over and over.
Yeah.
it'd be interesting if there's any quantification in like child development about like how long children spend looking at static objects versus like objects with behaviors. Because yeah, I wouldn't be surprised if it's like an order of magnitude difference in how long it can hold their attention.
Yeah, I wouldn't be surprised at all.
Yeah.
But yeah, maybe I'll move on a bit, because there's
Yes, let's do that.
things that we haven't discussed yet. Okay, so another thing we want to be able to do is to recognize a behavior at an arbitrary location, orientation, and scale. And the proposed solution for that is using exactly the same mechanism we're using for recognizing an object at an arbitrary orientation, location, and scale, which is to transmit this pose hypothesis down to the thalamus and use that to transform the incoming movement vector and feature inputs into the object's reference frame.
So a separate orientation for the behavioral model than the
Yes.
morphology model. Okay.
Yes, I know we haven't completely agreed on that before, but I guess that's what I'm kind of
Well, I mean, in support of that idea, first of all, it takes very few neurons to represent orientation, unlike location. And so it's a small population of cells, so that's not an issue. And we do have the different layers in the thalamus, which would suggest perhaps, there's these paired layers, perhaps they're paired in this regard. So we can accept that for now, I think.
Yeah, it seems, yeah, like you say, it seems like it should be possible to send another projection down and transform those on those relay
They may
cells
look like the
into
same
transform.
projection. I mean, just literally, an anatomist may not see them as separate. They're just two cell populations that are co-located. So
Yeah,
we don't have to expect to see physically separate projections.
right. Yeah. And it's such, I mean, generally just looking at this, it looks so beautiful because it's an exact mirroring of this mechanism, of the mechanism we have for object models, now for object behavior. And it gives us all these nice properties that we had for recognizing objects, being able to recognize them in any location, orientation in the world. And now we can do the same thing with object behaviors, independent of each other. And it just looks really nice in my mind.
It
So
also, yeah, it fits really nicely with so many things like, yeah, the movement coming in at the edge between L5 and L6, and also the L5 being the motor output, that, it makes a lot of sense that that would be where kind of behaviors are represented.
yeah. Okay, and then another requirement we had was to recognize where in the sequence we are and recognizing them at different speeds. So this is one that's we haven't totally settled on, but I think the general mechanism I'm going to propose here makes sense. So basically from the matrix cells, we get this timing signal. The matrix cells themselves don't know anything about the behavior model. They don't know which behavior we're recognizing, what we're sensing. They're just giving a timing signal, kind of like a metronome. And then here we learn at what click in the metronome should we recognize which features at what locations, or which changes at what locations. And then when we actually observe the sequence faster than we have learned it in our model, we are predicting the correct changes at locations, but they appear earlier than expected. So then we need some way to speed up that metronome. So I made that arrow red because I'm not sure where that signal would come from and how it would go to the matrix cells, but basically we see correct changes at locations as predicted by the model, but earlier than expected. So somehow we need to tell the matrix cells to speed up that metronome, and once that's sped up, everything works again.
I don't remember where they're coming from, but that projection back to the matrix cells exists. I talked to a bunch of scientists about it in the past, maybe I've been taught the past 15, 20 years ago. So those connections exist. I don't remember the source layer.
I can double check. I think it came out when I was looking at the claustrum stuff. I think it's from L5, which would fit potentially.
Right.
But yeah, I mean, in general,
Right.
like conceptually, it's basically like the same like scale and rotation. It's just like here we're scaling time
Right.
based on like an inferred, and again, we might have a bias towards expecting it to happen at a certain pace, but we can recognize it at an unusual pace by scaling it.
Yeah, and yeah, basically the pyramidal cells could detect that mismatch. So detecting a pattern on the basal dendrites, and then which depolarize the cell and indicate that the next feature should be arriving at this location now, but then apical dendrites don't get that matrix cell timing input at the right time, either too early or not at the time they expected it. And then I think, Jeff, in a comment on the documents, you suggested that potentially they could send like a back action potential up the apical dendrite to learn that expected timing and recognize the difference. But there should definitely be some mechanism in here to recognize
Right.
expected timing
There
difference.
has to be, right? There has to be a mechanism. I think the general idea of this matrix cells providing the time signal, adjusting, is very likely correct. Somebody has to do it. And the actual mechanisms are not as important at this point in time. Exactly how do the neurons detect the difference and transmit that difference down? Those are going to be things that maybe no one's even discovered yet. So we don't want to spend too much time thinking about it because there may be some weirdo property of apical dendrites that, no one's ever measured.
Yeah.
But
Yeah.
we know it has to exist. So we can just say, go on and say, great. It happens.
Yeah, so the conceptual mechanism is pretty simple, but we're not sure how exactly it happens in the anatomy. But yeah, just for the complement, if the sequence is observed slower, we again see the correct changes at locations, but later than we expected them. So then we need to tell the matrix cells to kind of slow down the metronome, and then everything fits again.
It's also
The
kind of
matrix
interesting because
cells,
like,
sorry,
go ahead, Michael. Well, I was, it's a slight tangent, so yeah, if you go ahead.
Okay, just I guess a clarifying question. The matrix cells and the metronome are a local clock to this particular behavior, and another behavior column has its own local clock?
No. The way the matrix cells work, well, first of all, they're not specific to any particular behavior. As Viviane mentioned earlier, they're sort of a global clock, and they project broadly over multiple regions within a particular modality. So matrix cells would be a set of matrix cells that project broadly over all visual regions, and another one that projects broadly over all somatosensory regions. And that makes sense because time is going to be the same for, you can't have one part of the object running at one time, another part of the object running at another time. That would be a different behavior. So you want this sort of global signal that tells everybody, hey, everybody, we're speeding up, we're slowing down, we're speeding up, we're slowing down. Everybody within some multiple region that are all observing the same object.
Okay, and then I'm just getting at, like, in electronics, a global clock is a very difficult thing because there's propagation delays as the clock signal moves across distance.
Right.
So you could take relative measurements, but you couldn't get an absolute time at two different locations and be assured it was the same time.
Right. But you got to remember, and there are propagation delays in neurons, but it doesn't really matter. The pyramidal cell that's shown up in layer 3 there, it doesn't know about propagation delays. It just says, hey, I became active. This is what the clock said at this point in time. Well, maybe the clock started a little earlier. It doesn't make any difference to that cell. The cell just says, this is what it is. And I don't care how long it took to get to me. This is what it is now. So
Yeah, okay. As long as you're not looking to extract the exact global time.
Nope.
Then you're fine.
What's important is
Yeah, and I think in general, the fuzziness of neurons and stuff, like, yeah, it's not going to be a perfect, but it's more just giving them a general.
It doesn't matter. The delays are no one knows about the delays. No one's keeping track. There's nobody saying this is time 0. It's just like,
it's just time has advanced approximately half a second.
I'm taking note of it. And if it took a millisecond to get here, well, so what? I don't know.
Yeah. Okay.
It doesn't matter.
Yeah, I was just going to comment on actually what ended up kind of coming up in this conversation, which is, yeah, just that it's kind of interesting how here it's kind of global, because exactly like you say, Jeff, like in general, an object kind of, it follows like a single kind of sequence of time in terms of behavior. Otherwise, it's becoming some other type of behavior. Whereas with rotation and scale, like we can have compositional objects where different parts of the child object are different scale and different rotation. So it kind of makes more sense than that we kind of have that as a individual column basis.
Here too, if we had multiple behaviors on an object, those behaviors could have different scales of time, right? So one could
but we'd have to, I guess, kind of shift between them. It would be kind of an intentional thing, probably.
When I first thought of this idea of the matrix cells, I was thinking again melodies. And within a melody, you basically speed up. You don't just speed up one note. You speed up all the notes. Slow down all the notes. And of course,
yeah, like if the drums suddenly started going really fast and everything else started going really slow,
it's all relative positions and timing. So anyway, this makes sense. It has to be a global signal to all the different columns that are participating. All need to know we're all being sped up or slowed down together. So anyway, I think this is great. We don't have to spend more time on this. This is the hypothesis. It's almost certainly right to the level you described it.
Yeah, and talking about global signals, we also want to be able to use multiple columns. So then the last part missing in this picture is voting. So similar as how this morphology model can vote on object ID with other columns, the behavior model can vote with other columns on the behavior ID. And then I kind of put state in the sequence here a bit in between, because first I thought we could also vote on the state of the sequence, but then I thought this information is probably already contained in the matrix cell signal. I'm not sure if that would be something we could already get from that timing signal.
I don't think so. I
Since
think we should spend time on that later, but I don't think so.
Yeah, okay, then maybe we would want to vote on the state in the sequence as well, or like which point in the sequence we're in. Okay, so that's kind of up to the point we discussed so far. Basically a solution for modeling an object behavior and recognizing object behaviors in a very flexible way. Does that make sense to everyone so far? Because now I'm kind of gonna go into the more suggested solution territory.
It's pretty cool to see. Looks like you guys made a lot of progress.
Yeah, for sure. Okay, so solutions for the remaining issues. Again, I'm going to do a quick revisiting of existing theory. So I think as a prerequisite for understanding these solutions, it's useful to revisit how we think the brain models and recognizes compositional objects. So again, we have one column that recognizes an object. In this example, it has learned the TBP logo mark as these features at different locations relative to each other. And now we introduce a second column, a next higher region in the hierarchy. And this region will get the object ID that was recognized in the lower column as a feature input into layer 4. It can also get direct sensory input through thalamus, which gives it information about sensor movement, and it could receive direct sensory input from a larger receptive field than the lower column. And together it can then learn a model of a compositional object, for instance, a cup. So just using this pink and solid blue line, it could already learn a model of a cup, but it would have to pay pretty close attention to these details here. And now using this connection, it can simply assign the logo to a location on the cup, and all the details of how the logo looks like are stored in this model down here. Is that clear?
Yeah, although the one small technical thing, it's not assigned to a location. The logo is assigned to multiple locations on the cup.
Right.
Multiple locations on the logo are assigned to multiple locations of the cup, which was required to solve a whole bunch of problems. We don't have to go into it, just for posterity, it's not assigned to a particular location.
Right, yes. So yeah, every location on the cup where the logo exists in this model here will store logo. It will keep getting this input and store it there. So it's not just one point for the logo in this model, but multiple points. And additionally to storing that the logo exists at these locations on the cup, it will also need to know the orientation of the logo relative to the cup. And for this, the proposed mechanism is that we can take the orientation in which the logo was detected and the orientation of the cup and calculate the difference of the two. And that difference will then be the feature orientation input to the higher level column. So yeah, this delta orientation is basically this orientation here minus this orientation here. And it's the orientation of the logo relative to the cup. That way, if the cup rotates, it automatically compensates for which orientation we would expect the logo to have. And we can recognize the cup in any orientation and the logo. And now we also want to be able to make predictions. So if we recognize the cup, we want to be able to make predictions about the logo down here. So we can have these classical backward projections from layer 6A down and then all the way back up to layer 1. There can make some synapses over here in layer 6A, which can tell the lower level model. It basically says, if I'm here in the cups reference frame, expect to be at this location in the logos reference frame. So it might tell it, oh, you're probably on the center dot right now, which will then tell the lower level which features to expect. And then also up here, these apical dendrites from pyramidal cells in layer 3 can get some information about the higher level object that's being detected.
Hey,
And
Vivian,
then-
what would that information on layer 1 be used for? I'm not clear about that.
So yeah, the idea would be that this can inform object ID detected down here, since that's what's in layer 3.
The layer 1 projection it goes beyond the single column. It goes over many columns. And so it's better, sort of like the cup is saying, hey, multiple columns should be looking at the logo, right? I'm biasing you to look at the logo, but only the columns that's co-aligned with these two columns that are shown here are co-aligned. And therefore that those synapses in layer 6A, the purple dot in layer 6A, that says at this point in the cup, you're going to be at this point in the logo. But at this point in the cup, I can't tell what other columns are going to be. So you can bias the other columns to say you should be looking at a logo, but only one column can you say this is exactly where you are on the logo. So
Got
it's helpful.
Thank you.
And another question, is it really telling us or informing what the object ID should be, or inhibiting unlikely object IDs? Because these are inhibitory neurons, right?
Which
in
are
layer
inhibitory neurons?
layer 1 neurons.
These aren't layer 1 neurons. This is an axon from the layer 6A cell in the second column. So those are those are axons from excitatory cells. And if they form synapses on the apical dendrites, as shown, there's a little pyramidal cell in layer 3, right? Those would be excitatory synapses. So those would be exciting the layer 3 cells, biasing it. There are some cells in layer 1, and some of those are inhibitory, but we're not talking about those at all.
Okay, so
not-
the
not
the
shown
layer
here.
6, the layer 6 in region 2 is not exciting or making the inhibitory neurons in layer 1 fire.
I didn't say that. I just said we're not saying anything about inhibitory neurons in layer 1. We have no theory about them. So all that we're saying is that a very well discussed connection is that they make connections. In fact, hardly anyone ever talks about layer 1 neurons, but there are some, not a lot. There's some, but we're just talking about the very well known connections between the layer 6A axons and the layer 3 apical dendrites, and those are all excitatory. And we don't have a theory of what the inhibitory neurons are up there doing.
And then also, since these locations are unique to the respective objects, so this location is unique to the cup and this location is unique to the logo, if there's a connection between those two, this cup will directly inform the logo model itself about where it will be.
Right.
That makes sense. Yeah.
Any other questions?
We're still in review. I can't wait.
No,
I don't wanna
we're
run out
back
of
in
time.
review.
I don't want to run out of time.
Okay, yeah, I'll move on. So lastly, we also want to inform the lower level column about at what orientation it should expect to see the logo. And for that, a proposal we have is that that information is basically taking the orientation we stored in the model up here, the orientation of the logo relative to the cup, and adding it to the detected rotation of the cup. And and then sending it over here. And the idea is that this could be done by layer 6 cortical connections that are observed, and basically communicating the orientation that should be expected here for the logo by taking the delta orientation stored in the model here and adding the detected orientation down here. That's the proposal.
That's a more speculative proposal, so we
Yes.
shouldn't hang our hats on it, but it has to be done. And so we should just feel confident that it's done. This could be how it happens.
Yeah. Yeah, I think it's a pretty general mechanism. Like, I think these calculations would be the best way to do it, but it's kind of, yeah, I'm not sure if this.
No, I think the speculation is as to what cells are actually doing it exactly where.
Yeah,
I mean,
exactly.
specifically, the layer 6, say, the layer 6 cortical connections, there's a whole bunch of weird ones like down there. And I mean, they just fit the bill because they seem to go where we want them to go. But there's not much beyond that.
Right.
It's okay. It's a good placeholder. It doesn't, I don't think it impacts really any of our theories. It has to be done. And therefore there's going to be a connection to do it. And so it's a good placeholder for it.
Yeah, it almost, I mean, yeah, maybe we should get distracted, but it almost feels like you could also just further transform the thalamic input to the previous column. Sort of
Send it
bypass
down
it.
here.
Like rather than sharing it with, I don't know if that causes weirdness. Anyways, yeah, it doesn't
I
matter.
don't know.
Yeah, then we would, I guess, need to know if there are connections from the like V2 to first order thalamic nuclei.
Yeah. Yeah, I don't think we should spend more time on it.
Yeah, okay,
The
I'll
function has to
move on.
occur. We have to do the same for scale. Scale is going to be relative. It's going to happen. We know what happened, so let's just go on.
So yeah, now on the topic of learning associations between objects and behavior. So we want to be able to see a behavior and bias which object we detect. One object can have multiple behaviors, and behaviors can be in an arbitrary location, orientation, and scale on an object. Does that sound familiar? Yes, it sounds kind of like learning compositional objects, where one object is made up of multiple child objects, and child objects can be at arbitrary locations, orientations, and scales on the parent object. So why not use the same mechanism to solve this problem? So the proposal here would be, we have a model of the object, for instance, the stapler at the higher level column, and we have a model of the behavior at the lower level column. And the detected behavior ID essentially becomes a feature on the higher level object at a location and orientation on that object. So same as we assigned the logo to the cup using this connection, this feed-forward connection, we could assign the hinge behavior to the stapler. And then additionally to tell it the orientation of the behavior on the object, we do the same thing. We calculate the relative orientation of the behavior to the object model down here using these two projections, and then send that up here as the feature orientation input. Does that make sense?
Yeah, the first question that jumps to my mind is the projection of the layer 4 in region 2. Would there be a case where you're projecting both a child morphology object and a child behavioral object at the same time? Does that ever occur?
You
I'm
could.
not sure.
Yeah, you could, for instance, say I'm on the top of the stapler here and on the bottom of the stapler as the projection from the lower level column, like if we have segmented the stapler into top and bottom. So that would be the input here as an object
Yeah,
ID.
or
as
I'm
a
thinking
feature.
like, what if the logo had some behavior? The logo can rotate 20 degrees back and forth or something, you know. But okay, I think it works. So I'm just thinking out loud.
Yeah, I think
Okay.
so far in my head, like when we've kind of thought through this, how to like generalize with this, it makes more sense when the morphology model is the child and the behavior is in the higher level column. But But
we did. We
but-
remember we started with that, Niels. We started with the idea that, oh yeah, within a column you could assign the behavior to a different object.
no, I'm talking about two different columns.
Yeah, I know. And then we came across the idea of, oh crap, it could be just like what Vivian just said. There could be a child. There could be, you know, these are child objects because you have multiple behaviors per parent object. You could have child objects, and so where I was left struggling, and maybe Vivian's going to get to it. We had these two proposals. One is that behaviors could be applied to an object within a particular column, or as hierarchically as shown here. And
I'm proposing doing it hierarchically here, and I'm doing it as behaviors on the object because usually, as we also I think talked about before, is that the behavior is usually kind of smaller than the object itself or applied to part of the object. So it makes sense that this is on the lower
at one point,
column.
Vivian, you were saying, oh, but you love the idea of doing it all in one column, and so you were a little hesitant to give up on that. Have you given up on that? Have you said, okay, we don't need to do that?
Yeah, for this issue of assigning behaviors to objects, I think it's nicest to do it hierarchically because it's exactly the same problem as learning compositional objects.
I'm trying to jump ahead. Are you going to abandon any idea that would be within a column? I'm okay with that. I'm just trying to understand where you're going to head. Okay.
Yeah, in this proposal, there's no association within the column.
I kind of feel that my gut says that's probably the right way to think about it. Okay, good.
Okay. We also want to be able to see a static object and infer behavior. So we see the stapler standing on the table and infer that it can move up and down. And so for that, again, we have the same setup, the stapler model here, behavior model here. We could simply use the feedback connections where if we have recognized the stapler down here, we can inform the lower level column to sense the hinge behavior and also to where to expect to be in that behavior's reference frame.
It doesn't tell me where I should be, or does it tell me where I should be in the sequence of the behavior? It tells me definitely like this point on the stapler has a potential behavior.
Yeah, usually if the object is static, the sequence hasn't really started yet. It's more like you could sense this is a potential behavior of the object.
Right. Okay.
And I guess this would be probably something that would also happen within a column, right? For like a familiar object and familiar behavior. The two.
Well,
if you go back to the constraint.
That's the question I just asked a second ago.
Yeah, but I think there's multiple things that we could argue about which things can happen within one column and which things can happen across multiple columns and which things might be in both. But specifically biasing the recognition of behavior based on a morphology, it seems natural that would also happen within a column.
Oh, you could do it within a column, but I just didn't see a need for it here because it's already solved with the feedback connections.
But what about the instance where the behavior and the morphology are learned within the same column? Like here you're showing it across multiple columns because you're generalizing to, like, this is assuming we haven't learned the behavior for the like, stapler, right?
Let me take a stab at that, Niels. It's a little bit like compositional objects. In compositional objects, we assume that the two columns, meaning the two hierarchically arranged columns, both can or actually necessarily learn both sets of objects. Like the upper column can learn a mug and the lower column can learn a mug. And the upper column can learn a logo and the lower column can learn a logo. Therefore, I can observe a logo on the mug and I can observe a mug in a logo. That would, the same thing would apply here. We would have, if we took that same idea, we would say these two columns would both learn might both learn the morphology of the stapler, and they might both learn the behavior of a stapler. And therefore we could say, oh, well, this is a stapler which has a hinge. That's a subset of it.
Yeah, I think the main argument that I forgot about is that if we do it within a column, we can't do relative reference frame transforms there. We can't say this behavior should be in this relative orientation to this object, like we can do in the compositional setup. It's like doing compositional object within one column where we say the presence of the logo biases the presence of the TBP mug.
Right.
But we can't tell any more about like which locations it should exist at and which orientation it should exist at. Whereas in this
Sure.
setup, if we do it hierarchically, we can inform all that.
There's a
I
parallel there.
agree with all that, and I agree it makes sense to have it across multiple columns. I'm just saying that, have you totally gotten rid of having, because as you just said, Jeff, like you will learn like potentially both in both columns.
But there's not a
Like
connection between the two. Like when I
within a
learned,
column,
not within a column. We
why
went to
wouldn't there
this-
be?
Well, we went to the same transition with morphology objects. At first, I resisted the idea of using hierarchy. I said, look, a column should be able to do everything on its own. That's one of my, things. And then, but then we kind of did this, no, it can't. And then it's like you have to rely on hierarchy for doing composition. It doesn't violate the columnar hypothesis. Every column is learning compositional objects. It just doesn't know what the child objects are. That's the answer to that one. So in the same way here, we started off by thinking, oh, we could learn this all within a single column. They're right there. They're right on top of one another. Isn't that wonderful? We could apply the behavior learned in this column to a new object in the column. But then realizing that the hierarchical solution is more powerful for the reasons Viviane just mentioned. And so the question is, why would I introduce it back into a single column? I mean, just like we started trying to do morphology in a single column and I abandoned it, we're not trying to do that anymore. And I think the same argument would apply here. It's a little counterintuitive initially, but it's a more elegant and powerful
I think
solution.
it's worth moving on to, like, I think the point I'm trying to make is not a particularly important one. It's just this particular question of biasing the recognition of behavior that I think to a certain degree that could still happen in addition within a column, but I don't think it really, it's not a big point. So
Viviane's point is that this solution solves I think it's going to solve all those problems. You don't
yeah, I'm not
need
saying
to
it's
composite.
necessary.
Right. And then
I just think it's it might
but if you
improve the
introduce it
performance of the
there,
system.
then you're going to be introducing problems like, well, it doesn't work in this situation, it doesn't work in that situation, it has this issue.
Yeah,
So
maybe.
I think it's a valid point, Niels, to say, well, maybe there's one way I look about this is that neurons, they form synapses with anything that makes a Hebbian sense, right? They're kind of stupid. They don't really know what these axons are. So it may turn out within a column, if these axons are passing near other neurons, that they'll make connections that we don't really need them to do, but they don't hurt. So that may actually happen, I think, but we should follow the logic of first the whole theory of how can it be done hierarchically, then come back later and say, well, did it miss anything? Is there anything we need that it didn't do yet? And I think it would be I think that's what Viviane's recommending.
Yeah, no, that sounds good.
Okay, let me move on to last points. I guess just for curious viewers who saw this kind of dot here and were confused why that's there too, it's just kind of
Which dot?
Here,
that one right
the
there,
feedback
yeah.
projection. It's just kind of
Yeah.
for completeness because this is still the morphology model. So this feedback connection, as we've shown it before, also biases locations in the child object's reference frame. So here, like you touched on earlier, Jeff, this column might actually also get feed-forward input of the object ID of the child object. So like the top of the stapler. And then the same feedback connection that biases or that informs the behavior that exists at this location can also inform the child object that exists at this location.
Can I make an observation? It's really a question.
Yes.
Because I was doing sort of this chart of all the possible ways this could work. And one of the things they're suggesting is that there is an asymmetry here in the sense that the feedback connection is only coming from the full morphology model. There's no feedback from the behavioral model. And I think I think that's right, but I don't know if you agree with that. That is the higher morphology model can predict behaviors and predict components. But there is no sort of hierarchical behavioral model. Is that correct?
Yes, I think so. Let me come back to that in a bit. Hang on, I thought about it yesterday, and I think I came up with a purpose for a feedback connection from the higher order behavior model, but
Well, that would be like a projection from like, if that was in layer 5B, then it would be a
Yeah.
projection from layer 5B back, like the purple.
oh, I think I will show it in
Okay.
a future slide.
I couldn't come up with a reason for that. I couldn't come up with a reason why a behavior model had to project backwards. But I
Okay,
didn't really think about-
it'll actually come up next,
Okay.
I think. So yeah,
All right.
so I'll get back to it in a moment. Oh yeah, and then also we can use the same kind of cortical layer 6 CC connection to inform the orientation at which the behavior should be observed.
Quick question. Does
Yes.
this solution help us break up the objects? So the way I see it, we've learned, so in region 1, we've learned the movements or the behavior
Yeah,
on the stapler.
I'll also get to that in a moment.
Okay.
All to come. Okay, so this was the chapter about, or the part about learning associations between objects and behavior, and basically the proposed solution is to use hierarchy for that and use the same mechanism we use for compositional models. Now the next topic is this big one that we struggled on the past weeks, is how do we make predictions about an object at an arbitrary point in the behavior sequence without learning keyframes. And I'll first look at it for an object and behavior combination that we know. So we learned the stapler opening and closing, for example. So now here, you notice I'm showing the different combination. In the last slide, I showed the morphology model up here and the behavior model down here. Now we're actually recognizing the morphology model of the subcomponent here, the stapler top, and the behavior of the stapler opening over here. This is kind of irrelevant, just as FYI, this higher level model would have then the model of the complete stapler where the top is a feature on the stapler. And so let me think through this again. Did I explain it correctly? Yes, okay. So what would be a behavior at this higher level? So one thing that can happen is we have the orientation of the child object and the orientation of the parent object, so the stapler top and the stapler. And normally that's kind of a fixed thing, and that relative orientation becomes the input to layer 4 mini columns. But if we have a moving object, that can actually be changing. So suddenly this relative orientation is changing. So now this will become the input to the behavior model. So now exactly same.
What becomes the input to the behavior model? What is that?
The change in pose of the child object relative to the parent.
Is it a change, or is it just the current orientation?
No, it would be the change, because the behavior model only gets changes as input. So it doesn't get input if there's nothing changing. So if we just have a stapler sitting there, we calculate the relative orientation of the top to the stapler, and that becomes the input to layer 4, to the morphology model. We assign the stapler top to the full stapler model here. But if the stapler top now changes its orientation because the stapler is opening, whatever we are calculating here is suddenly changing, and that change in pose of the child object will then be sent to the behavior model.
Yeah, I think that makes sense.
Yeah, there's some holes in my thinking about it. I'm trying to think like, oh, well, there's orientation is represented by mini columns, and so would these be mini columns, or would these be features of the would these be features of the behavioral model? I think these would be
Yeah,
features.
so how I imagine it is that it's basically the same mechanism as we use at the lower level for the behavior, where we detect changes by like temporal offset of on-off cells in the thalamus being activated. Here we have temporal offset of relative orientations changing, and that kind of encodes an orientation change that then activates mini columns here. So same as here, we would detect a rotating bar or a moving bar. Here we would detect kind of this relative orientation changing.
All right, I'll have to think about it sometime.
And yeah, so that's kind of, for me, it answered a couple of questions. First, like what is even the input to behavior at a higher level? Because it only receives changes, not features. So the behavior ID is a static feature at this point, so that needs to go into the morphology model. It can't go into the behavior model. But this kind of answers this, that if now the pose of the child object is changing, that suddenly becomes an input to the behavior model.
But
And
that's only the orientation of the features changing, right?
yes.
I mean, but other things could happen. It's not just the orientation. It could be appearing or disappearing or just changing in any way.
Yeah, so that would be other kinds of changes. So for example, I don't think I show it in this graph, but if for example the object ID changes or the behavior ID changes, then that would also become input to the behavior model. Like if I have a red light that changes to green, or that's not too complex, but if you have an app on your phone and you press it and the icon changes, then it's a new icon ID that has changed when you pressed it, and then that change would be an input here.
So the goal of this exercise right now, we're trying to predict what the morphology of the object will be based on its current behavioral state. Is that right?
Yes. So this is kind of a preamble to that. So basically,
Oh, okay. Because like I said, I don't think you've solved that yet.
no, I didn't. But this
Okay,
is just
okay.
defining what is stored in this behavior model. And basically, the idea is that the behavior model stores changes of the child object's location and orientation. So basically, here now in this behavior model in the higher level, we store that the top of the stapler is changing its orientation over time. And we can then, for one, we can use back projection, which tells where we expect to be in the child's reference frame. So which features to expect. And then we can have, again, this layer 6 CC projection, which tells which updates the expected orientation of the child object. So basically up here, we store the changes in the pose of the child object, which is kind of the behavior model now. And now we can project these changes over here and through the sequence of behaviors, update the expected orientation of the stapler top. And then all the predictions about morphology, about which features to expect, are made down here using this learned model of the stapler top. We don't have to do anything. We just adjust at which orientation we expect it to be using this feedback projection. And that transforms the incoming movement vector and the incoming feature vector and lets us make predictions.
Yeah, I mean, I think that makes a lot of sense. I think that's kind of fits with intuition of how this would work, and yeah.
Well, it's good. I mean, my assumption that somehow this would work, but I think you're putting some meat on it.
Yeah, I think it's promising. There's one big issue with it that I haven't mentioned yet, but yeah. The main big issue is that this only works for orientation changes of the child object. It doesn't work for location changes. And I think the fundamental issue there is that nowhere do we ever communicate the location of the object relative to the sensor or the body.
Hang on, what do you mean by location change?
Yeah.
So let me think of an example. I mean, I guess it just seems like we can have object behaviors where subcomponents are changing their location and not their orientation.
Well, it's interesting.
Yeah.
Would that be more kind of like a location by location basis? Like you kind of have to break it up, and then those are going to be different associations. I mean, yeah, it would help if we had a specific example, but just
yeah, I guess if you think of a pot as a compositional object and the lid goes up and down, it's not a perfect example because then
Well, you could take the stapler. Take the stapler instead of having a hinge. Let's say the whole thing, the top just extended up and then extended down. Same idea.
Yeah.
It's still connected somehow. It's like your pot, but instead of hinging, it's moving.
Yeah.
And it's not clear to me right up front why that.
That's fine, isn't it? Because so the movement in or like the behavior in the higher level column tells us that, okay, after this behavioral state, we'll be at a new location. But it's kind of like what we were talking about last time. Like as long as there's a way that location is common in the higher level column, it's still going to predict the right location in the lower level model, and therefore predict the right morphology. I think the tricky thing is like
yeah, I mean,
understanding how behaviors in the higher level column like actually represent changes in location.
I mean, we can bias the location in the object's reference frame that we want to expect, but we can't really communicate that the object is in a completely new location now relative to the sensor.
It's too much for me to absorb right now. So it's not clear to me. It doesn't work.
Yeah, we can leave it at this and say that it's. I mean, maybe we can make it work for location as well. I think it's a nice solution for making it work for orientation changes, and I think it's a nice solution to make predictions about object morphology. Basically making all the morphological predictions using this morphology model, and the behavior model basically just rotates that expectations.
Well, again, I'm not sure why it just has to be rotating. I mean, you're saying it's not clear to me that it won't work for locations as well. But
yeah, maybe I'm not thinking hard enough about it, but maybe worth like a Excalibur brainstorming session.
Well, I think we have to figure out exactly how it fails, or it's not obvious to me. I can't absorb. I mean, what you presented today is great. It's sort of like flushing out details of one of the ideas we've had, right? And now putting a lot of meat on it, and so that feels great. It feels like, oh, this is great. I love this. But I haven't internalized what the implications are yet of that, right? It's hard for me to internalize all of that in one, 20-minute presentation of this particular idea. So I'm just saying I'm not able to say, oh, it works or it doesn't work. Oh, I see the problem. I don't see the problem. It's more like, oh, I have to spend some time working through this to understand it better.
Yeah, maybe I'll just wrap up the last slides because we're already a bit over time, and then I can share the presentation with the slides on kind of what I think are open issues, and then we can talk about those more in the next meeting after it kind of settled a bit. That sounds good.
Yeah.
So yeah, basically I kind of put a grayish check mark here because I think it solves it, except for location changes, but maybe it can do that too, and I'm just not thinking of it. And then the next problem to solve would be to make predictions for a behavior applied to a known object, but a new combination. So we've never seen that behavior on this particular object before. So for instance, we have a book down here, and we've never seen the book opening. So we're detecting this kind of opening behavior, and we want to make predictions of how the book will look when it's opening. And so we can use the same mechanism of sending down and changing the expected orientation of the book. But we would kind of have to apply this temporary mask that we talked about before, where since we haven't learned a like compositional object of the book yet, we haven't recognized that like this part of the book can move independent of the other part, we would basically want to make predictions about the book changing orientation, but only for part of the book. And that kind of where this attention mask is applied could be informed by which parts are moving. So basically, we only want to make predictions about the parts of the book that are moving. And that could be the heuristic for that. I'm not sure how that would work on a neural level or which kind of connections we would need for
We
it.
had this has to happen for the stapler too, right? I mean, it's
Yeah.
right,
Before we
it's
have
basic.
learned the subcomponents.
This is the idea that how do we determine that the top of the stapler is a separate object?
Yeah, exactly.
And the assumption has to be that the lower column has already learned the complete stapler or the complete book, and now we're just gonna mask off part of it while it's moving.
Exactly. And then, yeah, over time, this mask could be used to then learn a compositional object. So learn that this is a subcomponent on the high level book object and help
It
us.
seems like we learn this very quickly, so this isn't a slow learning process.
Yeah, okay,
This
yeah.
observation.
Yes, you could.
This can be learned in 1 or 2 exposures, and you go, oh yeah, I get it.
Yeah.
That's
But yeah, so this would be the proposal for applying behavior to a new object that we haven't segmented yet. I think it's a nice mechanism, but also a few things that still would need to be worked through maybe.
Oh yeah.
But yeah, it would at least solve the general problem.
Yeah, no, I mean, I think it definitely feels like it's along the right track. I think or yeah, maybe we'll get to this, but yeah, I think it's the location representation in the higher column in the behavioral reference frame. I think the nature of that is kind of key because kind of by definition that's changing if we're going through behavioral space. So how do we then maintain an association with the morphological model in the lower reference frame?
You mean this location is changing?
Yeah.
Moving the sensor, but then wouldn't this one move as well?
Yeah, exactly.
I think it would work with
we
regarding
move
the
to a
same
new
movement.
location. Like let's say we saccade, so we expect after like with the open thing that now it's going to be somewhere else.
Yeah.
We haven't made an association. Like that's why I feel like there's almost like an association between the behavioral model and the morphological model in the higher column, and then between the two morphological columns, because that's at least fixed, I think. And so I think that's why you need the morphologies to be similar. Like you can't really expect, like you can't really apply like I don't know, like you can take a clam-like morphology and apply the hinge behavior, but you can't apply it to like a box unless there's suddenly a seam in it.
Yeah, I mean, maybe I'm missing something you're saying. I guess something to also point out is that notice here I haven't drawn the feedback connections in this example. So there's no association between this location in the reference frame to this location in the reference frame. Because we can't know about this at this point in this scenario because we've never seen the book with the hinge behavior. So we can't really have this kind of location association learned either between two columns or within the column because it's like a novel combination. I don't know if that maybe.
Well, when we learn it and I guess that's the other thing is it maybe fits better with the anatomy that it would be an association from the morphology model in the higher level column, which just like when you learn a compositional object, like you see a logo for the first time on a new object, you look at it, you attend to it, you can learn that connection immediately. But then that enables you to generalize to when the model causes the object to deform. That's at least how I was thinking of it, that it's like it is a learned association, but it would be in the L6 to L6 connection.
Between the two columns?
Yeah.
So you're saying
Um,
there would be like L6 between the two morphological models?
yeah, and then it's kind of like because the behavior is familiar in the higher level column, it then can you map from a behavioral point in space to a point in morphology space where it's familiar, and that tells you what is the corresponding point in morphology space in the lower level one, and then you're predicting kind of what you'd see after moving in that space.
And what problem would that solve?
This is for applying the behavior to a novel object.
Okay, but why wouldn't this mechanism be sufficient?
I guess it's just in terms of how you actually predict. Like maybe you're right. Maybe for orientation this is sufficient, but I guess yeah, for predicting other kind of changes that can happen in the lower level one, other than it just rotating.
Yeah, so yeah, if it's a solution to it changing location, then yeah, definitely. I'm not sure I understand it completely yet. Maybe we can draw it out sometime.
Yeah, I'm not. I don't think it makes total sense in my head. Like it's definitely just a rough, like a feeling, but yeah, it would be worth working through properly.
Yeah,
But no, I think you're right. I think maybe with orientation, it's kind of sufficient just to have this transformation.
yeah. Yeah, that's what I like about this mechanism so much is that it's really simple. It really just takes the stored orientation change here and sends it over here and applies it to the um, orientation of
Yeah,
object's reference frame. And then that takes care of all the predictions we want to make about morphology.
yeah. It kind of reminds me about something I think you talked about at the retreat, which was like, what if the behavior is like predicting a transformation, the change, and then kind of almost subtracting that in the thalamus or something like that. But here it's kind of more column to column.
Yeah. Yeah, let me maybe get to the last
Yeah,
point.
Yeah, yeah, sorry.
I want to see open issues.
Okay. All right. Just briefly, if a part of a behavior sequence is occluded, that's no issue because we have learned the behavior model and that sequence is just getting played through the matrix cells. We're not pausing it as we go through the occluded part. So we keep making predictions even when the book is partially occluded and we are just at the correct point in the sequence once it comes out of occlusion again. So we make the correct predictions. Basically, that metronome keeps on ticking even if there's like a black bar here. And then lastly, compensating for object movement when recognizing morphology is also no issue because, yeah, I mean, kind of what we talked about at the beginning, that it's kind of a sub-issue of the previous problem. So because this behavior rotates the expected orientation of the sub-object, that automatically takes care of properly transforming the movement vector and incoming features, so we can still recognize it even if it's moving. So that's that. Chapter 4, remaining issues. You all still have a few minutes to go through them? Okay. So this one is the main one that I see, or it's kind of two sub-bullets. How's the child object location change communicated to region 2? So we have a way of communicating that the relative orientation of the child to the parent is changing. We use this kind of relative orientation calculation and communicate that change up here. But what if the relative location of the child to the parent object is changing? I don't have a good answer for this right now. One random idea I had would I could use the layer 6A projection.
I still don't understand this problem well enough. And even with the stapler top, it doesn't seem like, the stapler top doesn't, in a compositional idea, it's not it's not one location there either. I mean, parts of the tabletop are moving relative to the other parts. The orientation, remember, we apply this at a point by point on the point by point. So I guess I'm not see this as a separate problem, or maybe you haven't solved it in the early one. I'm confused by this.
So basically, I'm thinking of the scenario where we have a child object that moves relative to the parent object. Right. Have a pen and we press the back of the pen and the tip comes out. And so that movement of the child object relative to the parent, I don't know where this information would come from. We can detect relative orientation.
I'm saying the stapler top is the same thing. The stapler top is it's really not just an orientation change. It's the location of parts of that stapler top are moving. It's not just there isn't an entire thing that's orientation.
Yeah, I guess like one way of maybe phrasing it is if it was literally just the orientation, the top would pivot on a point in the middle.
Yeah, I'm not saying
we're
solving the stapler completely either.
But maybe to clarify, so everyone's talking about the same thing. Like that's just one way of conceptualizing.
I think it's even worse than that, Neil. It's not that it would rotate in the middle. It's just that we only define rotation at a point by point location. Remember that remember the logo on the cup that took a bend. So that's the way it works. There isn't. I don't think it solves it. I don't think you've solved it for the stapler top either. So
I agree. Yeah, it's not solved for the stapler top either. So I'm just stating the problem that I don't know where changes in location of the child object relative to the parent would be detected and where it would be communicated.
All right, it was a good opening. I think there's some more filling in here we have to do on this.
Yeah. So yeah, I guess just two possible options I put in here was like layer 6A projection, because there's a reference frame there. It's not great because I don't think it projects to the higher level thalamic region. I'm not sure. And then another option could be layer 5A, because that one is already in the global reference frame, like relative to the body. So it would be much easier to calculate the relative location change. But it's also not great because here we kind of want to share the goal state and not the current location of the object. So those are just the two I could think of. I'm not a fan of either one, but yeah, open issue, I guess. And then related to that, how can region 2 communicate the expected child object location back to region 1?
Isn't that the same problem in some ways?
Yeah, it's basically the same problem, just the backwards connection. If I know the behavior, how do I tell it to expect the child object at this location? So it could be like a similar way of projecting the change that's stored in the model down here somewhere, and then we can communicate the expected location of the child object over here. But yeah, again, this is quite vague idea, and I don't really know.
Yeah, again, this is where it feels like the L6, like the normal feedback connection, could be a natural. If like L5 can tell that reference frame what is the particular, like L5 in the column 2, if that reference frame can tell the morphological reference frame where it should be, then that could.
Yeah, I guess the issue with the feedback connection I see is that is in the object's reference frame, which is specific to the object. So if we've never seen that object behavior combination, we can't possibly have those connections in the backward projection. Whereas here, I guess I drew this in black because I meant that this is relative to the body, so in like a common reference frame, and then we can transform it into the object's reference frame. So that way we could tell it a location of an arbitrary child object relative to the body. But
yeah, okay. I mean, we're assuming that we know the morphology and we know the behavior. We just haven't seen them together, right?
Yeah.
Okay. Yeah, so I think it could be done with like quick binding of those things, but yeah, I'm not sure.
Yeah, definitely want to think more about this and talk more about this one. And then another one is just how the attention mask would be applied to region 1 before the object is segmented. I mean, I think the idea of the attention mask is nice, but I'm just not very sure about what mechanism could be used for that on a neural basis. And yeah, I can use this heuristic of applying it to any part of the object that is moving. Have to think through if that actually works for any example we can think of.
It seems, by the way, it seems the solution to that, there's a general problem is like, what if I have an object that it's moving relative to me? And I still can recognize the object. So the stapler, as the car is moving, as you suggested, or the stapler sliding across my desk or whatever. If you understand how we do that, how we still infer that morphology of the stapler even as it's changing its location, then essentially I think you'll solve the problem of how do you break out the moving top. It seems to be the same problem. I guess I'm just thinking out loud about how I think you could solve that.
I feel like the first one is more an instance of like the last problem I stated of still recognizing object morphology even though it's moving. But there wouldn't need to be a mask applied to it necessarily.
Well, obviously, it's not a mask. It's more like, okay, an object is moving. I have to make sure that my reference frame and everything is anchored to that moving object. It's so its position relative to my body and its orientation to my body is changing, but I want to maintain the same model. But in this case, the model only applies to part of the object, because only part of the object's moving relative to my body.
Yeah, maybe one relevant thing, I think this was a comment from you at the retreat, Jeff, but it was kind of like, although there's there's almost a question of how much a mask there really is, because you kind of still see it as the object. Like if the top of the stapler is moving, you don't, I mean, I guess you can talk about the top of the stapler, but in some sense you just say the stapler is moving, like that part.
No, I feel that sort of the opposite. I feel once the top of the stapler starts moving, that's the only thing I'm focused on. I could come back and say, oh, is the rest of the stapler there? Yeah, there it is. And that would.
But I guess the point is like, it's still a stapler. So it's like, maybe we don't even need to mask that. Like maybe the masking, it's useful conceptually, but it doesn't actually need to happen for kind of the system to work.
At this point, we're saying it's a separate part of the stapler. All right, I want to make sure we get through all of your
yeah, so those are the big remaining issues I had that need a lot more kind of thinking and could break some of these ideas. And then I just have a couple of remaining uncertainties that are more like going back into the literature to read, and those are to point out what I'm not so sure about. So one is this kind of child object orientation change and how it can be, whether it can actually be communicated by these layer 6 cortical connections, similar to how we propose it for the compositional objects. I think in both instances, this is the least certain part, even in the compositional object idea. So just kind of, I'm not 100% sure if this is the best way to communicate this in the layers. And then, yeah, whether changes are actually represented in L3, because at least from like a lot of papers, it seems like direction sensitive cells are in V1 at least are usually found in layer 4 C alpha, which is the main target of the magnocellular pathway. So
yeah, maybe a brief comment on that. I wonder if like maybe a simple solution to this is like, maybe that's the direct input in the column, but then that's kind of processed into L3. And then that's why you see movement sensitive cells with narrow receptive fields in L3, even though the magnocellular input is in, say, L4 C alpha.
Just to bear in mind, if you don't remember this, there are people who have argued that the labeling of these extra layers is incorrect, that the different layers 4 are actually different layer 3s. So just some arbitrary decision to call them layer 4.
Yeah, I guess I'm just pointing out that like this exact layer assignment, at least I'm not 100% sure on, and yeah, whether layer 3 is the best one. And Yeah, I think this kind of whether they are direction sensitive cells earlier in LGN or even retinal ganglion cells is
Well,
sort of dependent on species as well.
Well, you're right. Remember that you don't really see them as, first of all, there are directional sensitive cells in the retina, but they're not transmitting, they're not ganglion cells, they're the internal cells. And it's believed they do other functions. But I think we assume that that information is not transmitted.
Yeah.
And
Yeah, I
of
guess
course,
just on a general note that, yeah, I think the mechanisms I presented here are pretty nice and general, especially for the behavior model, but like the exact assignment to layers, at least I'm not so sure about yet with the behavior model part. And then, yeah, another one I didn't talk about is how do we recognize change if the sensor is following the object? So kind of smooth pursuit where we have movement input, but no feature change. That's something you also brought up before, Jeff. And yeah, basically, how does this change information get into layer 3 or be compensated in the thalamus? And how would that mechanism work? And then this question we touched on earlier, how can columns share knowledge so they don't all have to observe every change in the behavior to learn it? Don't have a great answer to it yet, besides you do have to observe every change and repeat it many times. Another one is whether, like this is now for inference of behaviors, whether voting on behavior ID and pose is sufficient for fast behavior inference, or if we need to have some stronger mechanism actually kind of communicating movements between neighboring columns that are being detected. Because, yeah, behaviors can happen quite quickly. And then if you're just voting on their ID, you're not sharing a lot of information between columns to detect the behavior. But maybe it is sufficient. And then, yeah, do we vote on the point that we are in the sequence? So where in the sequence are we? Or can this be communicated by resetting matrix cells and kind of telling it we're at the start of the sequence now, and from there the clock starts? And yeah, just generally how timing is implemented by the matrix cells, how they are modulated for the speed adjustments, how do we indicate the start of a sequence or recognize it in the middle? Yeah, those are all things to ponder, I guess.
That's the last of them? Oh no, we got more.
The complicated world of the neocortex. Yesterday I spent all day just kind of putting all the connections into one diagram, so then I could build the slides and just remove the connections that were not relevant for the point I'm making. And yeah, this is how it looked like. So I guess the solution is not as simple as it might seem.
Yeah, that's pretty funny.
Nice. Yeah, that was a great presentation.
Can I just try to make it the most crudest summary I can? Those are great. I love it. I love the diagrams. It's very helpful. The first thing is there's really just a couple of the things you're proposing. One is, we talked about this earlier, that we really should be focusing on behaviors in a hierarchy and not think anything about what's going on in a particular column between the behavior models and the morphology model. Just focus on the idea that they are parent-child relationships. That was one, and that's a great clarification. That was like, oh, thank goodness you did that. I think that's great. The second one is, I think, was surprising me, was that basically the behavioral model ID was become a feature of the morphology model that was being projected to layer 4. That was a big insight that I don't think we discussed before. It may be obvious in hindsight, I don't know, but so that was really kind of cool. And then the third thing is this: okay, given those two assumptions, and you assume that the same mechanisms are in place for both the morphology model and the behavior model, which we kind of said before, but stated explicitly, then walk through all the issues. And so most of your presentation was just walking through all the issues. What happens if you make those assumptions, right? Which is great. I got lost towards the end there. I couldn't follow everything. I'm sure I'm not the only one. Well, maybe I am. I'm older, but
Oh, I got lost too many times
okay. So
making the
to
slides.
me, that was a huge. Those two things, eliminating thinking about within a column, is just like gets me to focus on hierarchy. Assuming that there are the same mechanisms everywhere, which we've said, but we never explicitly spelled it all out. And the same mechanisms between the two types of models. And then third, tying them together in some, like one, the morphology model projects to layer 4. I mean, the behavioral model projects to layer 4, the morphology model. That was like, oh, that's how you tie them together. And now you can tie them together with the back projections. So given all those things, I think this is a great, great start and a lot of great stuff in there. And so now it's just a matter of working out these details, right? And that can't be done in one first session like this. So at least not for me. But it's a huge clarification in my mind, just like simplifying the problem to eliminate things we don't want to have to think about.
Yeah, I think it was pretty nice how we can, like, that's why I added these two kind of preliminary sections about the existing theory, because for the first chunk of problems, we could take the existing theory about object models. And then for the second chunk of problems, learning associations and making predictions about morphology, we could use the theory about compositional objects. So I think that's my favorite part about this proposed solution, that it mirrors so nicely with what we already have.
So if the past is a prediction of the future, I think it'll take several rounds of discussions to work out all the details here. But I think it's the right path. So then the details are just a matter of turning the crank and working at it. And thinking through the problems a little more concretely. Like this issue of the moving of the staple top versus the changing the orientation, that really got me confused with what the hell's going on there. So, but I bet you we'll be able to solve all those issues with this clarification of the thoughts here.
I think if you
if anyone says observations, that was my observation. I don't want to shut down conversation.
No, yeah, I mean, if you're on board with the general ideas of using hierarchy for some of these issues, then our remaining problems, I feel like at least, become much smaller and more concrete. So,
but we, I'm not trying to take anything away from it. I mean, that was an idea we had. We just hadn't fully embraced it yet. It's like, oh wow, it's gonna be hierarchy like this. We already knew that behaviors had to be. You had to have multiple behavior models per morphology model, so it has to be hierarchical in that regard. I think it's. I mean, just stating it and putting in a picture of like, oh shoot, why? Of course, it has to be that way. Why was I struggling on this?
Yeah, and I think for me, another kind of takeaway or interesting one was just this kind of like relative orientation and what we can do with that, because again, it's something I think you was talked about briefly, but just kind of, again, as you say, Jeff, like putting into a figure, really kind of thinking through it.
Just stating,
extremely helpful.
Just eliminating some possibilities, stating this is the way it's going to be, and then just walking through the consequences. That's sometimes half the solution. Just like stop thinking about this other stuff, just focus on this one. And then we can keep going back to our, as you said, Viviane, go back to our existing solutions for hierarchy and say, okay, well, how do they make this work? Assume they're happening here too, right? What's going to happen? I'm still confused.
Yeah, and I feel that in general, it's just really satisfying that it can feel kind of insurmountable sometimes, these problems, but just how this kind of annealing process just can kind of slowly chip away at it. So, because if you think about where we were 6 months ago or something, it is definitely a huge progress.
Right. Well, that's why I made my comment earlier on when just reviewing the morphology model. I was like, oh, that was 10 years of my life right there. Because that was so hard. We didn't understand any of that stuff. It was just so damn hard to figure that out. And now this seems easier. It's like, oh yeah, we're just doing variations on a theme, It's like it's still hard, but it seems easier in some ways. Well, I'm going to think about this. This is great. I don't know if anyone else wants to talk about it, but
thanks, Viviane.
Stop being so long.
And now the diagrams are great too. All those little animations and everything is all really, really very, very cool.
Yeah, it took me like an hour to write all the notes, but then like 2 days to put it into slides because it's just so hard to communicate these ideas. Like it's all in my head, but then to put it into a way that I can
I
tell it
know,
to someone
I know.
else and it not be totally confusing.
Right, right. Yeah, well, those are nice diagrams. It's a nice new format. And if it worked for you, it worked for me. So. Okay. I'm gonna go back to the hierarchy paper.